All right, so here we're into 6.3 on the dual problem. So this is going to be minimization with problem constraints of the form greater than or equal to. So what we need to do is we're going to learn about the formation of the dual problem, solution of minimization problems, application, basically a transportation problem, and then we're going to look at the summary of problem types and solution methods, up to this point anyway. So, associated with each minimization problem with greater than or equal constraints is a maximization problem called the dual problem. So, what we need to do is we're going to be given a problem that's a minimization and we have to convert it to the maximization. So, that's when we do this. We form the dual problem. So, if we're given a minimization problem with greater than or equal to problem constraints, we're going to use the coefficients and constants in the problem constraints and the objective function to form a matrix A with the coefficients of the objective function in the last row. Then step two, we're going to interchange the rows and columns of matrix A to form the matrix A transpose, which again is called the transpose of A. Now, this is labeled as A superscript T, that's A transpose, and we're going to use the rows of that to form a maximization problem with the less than or equal to problem constraints. Now, the fundamental principle of duality, which is our theorem one in this section, is a minimization problem has a solution if and only if its dual problem has a solution. Now, if a solution exists, then the optimal value of the minimization problem is the same as the optimal value of the dual problem. So if the minimization problem has a solution, the dual problem has a solution. So it kind of goes back and forth. So that's why we're going to form this dual problem, which we know how to solve, but we have to go through this matrix transformation to be able to do that. Now, the solution of this minimization problem. So if we're given a minimization problem with non-negative coefficients in the objective function, then what we're going to do first is write all problem constraints as greater than or equal to inequalities. Now, this may introduce negative numbers on the right side of some problem constraints because you're going to have to multiply by a negative to get the inequality to switch signs. Then we're going to form our dual problem. Then we're going to write the initial system of the dual problem using the variables from the minimization problem as slack variables. And then we're going to use the simplex method to solve the dual problem. And then we're going to read the solution of the minimization problem from the bottom of the row of the final step of the tableau. So previously we would have our x1, x2, or whatever over here, and we'd read the answer on this side. Now we're going to read it from the top and look at the bottom row to get our answer. Now note, if the dual problem has no optimal solution, then the minimization problem has no optimal solution as well. Now, this is kind of a summary of all the types of problems we have up to this point. So we've got the maximization, which we're using the problem constraints less than or equal to, and the right side constraints have to be non-negative. And the coefficients of the objective function are going to be any real numbers, and we solve by simplex method with the slack variables. Now, minimization problem, which is what we're looking at in this section, we start off with greater than or equal to, and the right side can be any real numbers, and the coefficients of the objective function are going to be non-negative. And then what we do is we have to form the dual problem by taking transpose of A, and then solve by the simplex method with slack variables. So that's what we're going to do, and so that's kind of all the steps we have to do. And so I'm going to stop here, and then we'll come back with some examples.